Hey guys, we should probably get started because I've just been informed I only have 25 minutes and I planned on 40. So this is going to be a lot of fun. All right. There are other talks going on right now that have a lot more Python in them. This has 60 lines of Python total. So if you are more interested in seeing talks with lots more Python, I would suggest going to those.
Hey Randall, I just want to say happy birthday, dude.
God damn it. So my name is Randall. I work at Amazon. So my real name is Joseph, but I go by Randall. I'm Joseph Randall, so don't know why my name tag says Joseph. So we're going to talk about weather. It's going to be a little bit of a history lesson. It will hopefully be exciting. And I have to issue a few disclaimers right now. One, these opinions are my own and do not reflect the opinion of my employer for any legal or tax purposes. All right. There we go. That's it. So what was the weather like on the day you were born? I'm not going to actually ask you guys to answer this question because it's kind of creepy. So I normally have, at every demo that I give, a live demo and a prop. This time I have neither. My prop was going to be the hard drive that the live demo ran on, but I don't have that. So instead, I have this video where I'm going to explain what this does. So what we're going to do in this talk is tell you how you can build a cluster of MongoDB nodes to host centuries of weather data. And here you'll see what I'm doing is I'm putting in a point, and I'm putting in a date that is totally not my real birthday. And then I'm saying, find out what the weather was like, and then I say, go. And it'll start rendering all of this weather information. And you can't really tell because the resolution is terrible, and I'm really bad at making visual things. Also, if you ever do UI design, just don't ask me for help. But so originally what I was going to do is render only the things that fit within the geofence of North Carolina or of Raleigh or whatever place that I put in. But it turns out that the program we have is actually fast enough to render the data for the entire world. So we just did that instead. So that's cool. So I have an agenda where I'm going to talk about things, but I'm not going to go over it. So MongoDB is this very cool data store. For those of you who have never used it, you can think of the data store as a Python dictionary that you can query. That's how I think of it in my head. And that sort of abstraction layer lends itself well to dealing with the data. So it's a document data store. It has geo-indexing and things like that. Lots of really fun stuff. Blah, 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 blah. Marketing, marketing, marketing. And then simple sharded deployments. This is the vocabulary that we'll need to know to get through this talk together. So a database is still a database. A table is a collection. Rows are BSON documents. Indexes are still indexes. They're implemented by B trees and then other things underneath. And then joins, no. So now let's talk about the fun part, the data. All right. So we get this data from NOAA. So NOAA has $6 billion a year in budget. So they were founded in, I wish I had my speaker notes on here. That would be so good because then I wouldn't have to remember anything. Oh yeah, there we go. Cool. So NOAA was founded in the 1950s, but the NCDC, which is the National Climatic Data Center, which is part of NOAA, was actually founded in 1934. And it was started as a tabulation unit running out of New Orleans. And what happened was you would get all this weather data from all of these different stations all over the country and all over the world, and you would send it to New Orleans, and these guys would make little tables and then send it to commanders in the armed forces and be like, you shouldn't fly today. Obviously, this wasn't very efficient. Sending data over telegraph is very, very slow. So they started building more tabulation units and distributing their architecture. So it's the precursor to sharding almost. So eventually what happened is after Kansas City, Chattanooga, Tennessee, San Francisco, and a bunch of other places, they decided on Asheville, North Carolina, which is really cool because I went to school not far from there. And it's a beautiful, beautiful city. There's the Biltmore House, and then there's all kinds of great stuff. Just go to Asheville. So the National Climatic Data Center is hosted in the Grove Arcade building in Asheville, and they have an astounding amount of data. Astounding. You think the NSA is creepy. These guys are creepier. There's so much information about the weather. There are fields in this sort of weather data format that have things like, who was the president when this data was recorded? What could that possibly be useful for? So they have about 13.4 petabytes total. Obviously, I didn't use all of that because I'm poor. And they add about 200 new gigabytes of data every single day. So it's a lot of stuff. It's really cool, and there's a ton of it. Oh, and here's the part that I should probably mention. It's all free. So you can run a wget and mirror their site if you have a big enough hard drive, and you can just get all of that data for free. And so I run a couple parallel wgets and on AWS, and I didn't get sued. Oh, and then there's the World Meteorological Association or something that's in Asheville, North Carolina. So what happens is China, Japan, and like 50 other nations all send their weather data to Asheville, North Carolina. And these guys who have crazy statistics and cool supercomputers and stuff like that, they run calculations and build stuff, and it's really exciting. This is the machine that actually collects the data. Most of them are self-sufficient, some of them are not. This is what they look like. You can see they collect a wealth of information, and these are scattered all over the world. And they're different variations, obviously, because they're all built by different companies. But soil temperature and moisture levels and everything you could think about related to the weather that's not high atmosphere is calculated here, although they do have balloon data now, and I haven't figured out how to graph that yet, or like incorporate that, but I'm working on it. So all of this is powered by solar panels, which is pretty awesome. So what is in a weather datum? So a single piece of weather data, we have a station ID, which is either a US Air Force identifier or a W-band identifier. I have absolutely no idea what W-band stands for. It's just all over their manual, and they never actually define what it is. So a W-band ID or a US Air Force ID. They're also ships. And what I do with ships is I take the Latin long where they recorded a piece of information, and that becomes the station ID, for better or for worse. And then they have lat long elevation, and then there's a 135-page manual for parsing all of this information, which is in the most bizarre format you could possibly imagine. And I'll go over that format in a moment. So the cool things to focus on really are air temperature and atmospheric pressure and fire tornadoes and stuff like that. So how much of it do we have? We have about 2.5 billion distinct data points. I didn't go for 2014 because you have a lot more, so I just did 2013. So 2.5 billion distinct individual pieces of data. They're fairly small. They're around a kilobyte in size each. That ends up being about 4 terabytes on disk. And then while the number of documents is just mind-blowing, 2.5 billion different data points, the actual data size is fairly reasonable. 4 terabytes is sane. So I'm not going to call this big data. What I'm going to say instead is that it's moderately big data, or tiny data. So this is how it's been growing over the years. You can see, I don't know if I'm getting out of the camera if I'm ruining things, but you can see over here that in 1937, there's this huge, well, really 1940, whatever, 42, there's this huge sort of increase in when we start collecting data. And part of this has to do with the fact that we were going into World War II, and people didn't want to launch planes without any knowledge of what the weather was like. So that is when, people started realizing the weather was important. And the weather is important. I just want to get that point across. For those of you who don't watch Weather Channel, you're wasting your lives. So we get to 1973, and the proliferation of cheap semiconductors make it even easier to build all of these different sensors. And then we sort of keep increasing. And then something happens in 2000 where it just becomes insanely cheap to deploy these stations. And I think that's the advent of very cheap or cheaper solar panels. So you will see this huge increase in data over the past 10 years. So this is a zoom in on the past few years. This is their projected growth, and this is in terabytes, and this is in hundreds of gigabytes. I cut off the axis, I'm sorry, you can't really see it. But you'll see they just started collecting a ton more information every single year. There's just so much of it. You have everything from satellite imagery to topography to radar. And then I know there are a lot of particle physicists in the room, so I just wanted to say this talk will be relevant for you guys too. Don't worry, it's not just about weather. And it's also, yeah. So now we're going to go over Schema Design. I'm going to breeze through this because it has nothing to do with Python, and this is a Python conference. So there are a couple things we care about when we talk about Schema Design. What we care about are the performance, and the performance is sort of 3-tiered. It's about ingestion, it's about the app specific, so the queries that are running every day for whatever view you're rendering to an end user, and then ad hoc analytical queries. So you want to, if you're a scientist, what you're trying to maximize are those ad hoc analytical queries. Those are the ones you're trying to optimize for. And then the other two things you care about are cost and performance and flexibility. So cost is luckily linearly proportional to performance. So the more money you're willing to spend, the better your performance will be. And I'm about to demonstrate that point and possibly get fired. So flexibility, what I found with MongoDB is that you don't really lose any flexibility as you scale up. You might lose a little bit as you move into a sharded architecture, so that once you've moved into a sharded architecture, you've sort of made your decision about how you're going to be representing parts of your data. So that's the only time I ever really lost any flexibility as I scaled up. So these are the queries that I'm going to be running and doing in order to test those different points. This is the data format. And I know that everybody can read that and it's just completely clear what it is. So I'm not even going to bother telling you. This is weather data entry for New York Central Park. And then I built these little animations in Keynote and it took me forever. So, and it didn't work. So now I'm just furious. So essentially what happens is this sort of field here, which, by the way, is represented in a couple different ways in different places. So if you have data from 1890, it's not represented the same way as the data from 1990. You know, you have different, it's frustrating. So this is New York Central Park. And then you can see we have the air temperature value. By the way, you don't have any bounds for this, so you don't know if it's really 211 degrees or negative 21 degrees. There's just no info. You just have to guess. Great times, great format. Thanks. But then again, they're giving it all to you for free, so keep that in mind. Then there's this quality value. And what the quality says, it's not an increasing number. So 9 doesn't mean it's a better measurement than 1. In fact, 9 means insufficient data, or 5 means suspicious, and 1 means probably not right. You know, there's just a random array of different measurements that all mean different things. So it's not intelligent. So this is what a document ends up looking like. And you can just pretend that this is a dictionary in Python, right? And you'll see I have these sort of the station ID, and then I have the coordinates. And the stations, as I explained a little bit earlier, are either US Air Force IDs or WBAN IDs. And then for ships, I use the lat long. And then this format that represents the position is called Geo Json. I don't know if anybody's ever used it before. It's basically a rich format for representing geographical information in JSON, and it's readable. And there are a lot of different things that have support for Geo Json now, so it's a lot of fun to play around with. Yeah, that's what it is. There's a really good spec. I think Gustavo Niemeyer from Canonical is the guy who writes that spec. And if you go to geojson.io, there's a pretty cool viewer for GeoJSON information. This is what a typical weather piece of information looks like. It's air temperature, and it's negative 4.9, which is probably New York this winter. And that is in Fahrenheit. Nope, sorry, that's in Celsius. And then I have a bunch of speaker notes about what each number means for quality. And the reason I didn't store these as ints is because they're not really ints. So you have a couple choices when it comes to schema design. You can embed things or you can not embed things. In this case, we embed things because it's MongoDB. So one of the advantages of embedding is that you keep your application logic simple. You have the logic of the data inherent in the schema versus having a bunch of conditionals in the application. So that's cool. The next choice you have is around a unique identifier. I chose to use MongoDB's object ID in this case because I'm a bad programmer. So it's a simple guaranteed unique identifier across a sharded cluster, and it's only 12 bytes, which only really matters when you have 2.5 billion documents, which we do. So what a better identifier might have been would have been this, which is an embedded document that's unique on station ID and timestamp. The disadvantage of this is that despite the fact that this data is very high quality, there are duplicates. So there are 130,000 duplicates in 2.5 billion data points, which means trying to merge and solve all of those problems, where each one was its own special little gem of an edge case, was non-trivial. So I didn't do it. and instead I just used the object ID, and I accepted that there were 130,000 duplicates in my 100 years of data. That's like 0.00052%, so it's not a big deal. The other choice you have is around shortening the fields. I wouldn't do that because it makes it completely unreadable and storage is cheap. But you might do that if you were trying to optimize this and move it into a production environment. So this is what it looks like before it's shortened. And if you had to choose two candidates here for shortening these fields, I think the things that would really stick out are these values like value and quality and determination. Those occur a lot frequently. So you would, instead of representing those as quality value, determination, quality value, you could instead represent them as Q and V. Or you could just say everything is its minimal representation, but I can't read that, and why is that better than the format we already had? Aside from the fact that you can query on it. So one thing you might want to do with indexes is just prefer sparse indexes. This is all MongoDB specific stuff and has nothing to do with Python, so I'm going to keep going because I only have 10 minutes. This is the application. This is how the application works. So what happens is we have the data in MongoDB. The data gets, we query through PyMongo for the relevant data that we need. It goes to Flask, and Flask says, hey, we're going to shoot some JSON over to the Google Earth browser plugin, and this line is a lie because really it goes to JavaScript, and the JavaScript posts it into Google Earth plugin. And then Chrome and Google Earth plugin work together, and they render this representation of the weather data. And you get to choose pretty little icons for cloudy days or sunny days, whatever you want. There are a couple different ways of doing this. You could do this with a straight query in PyMongo. What we did instead is we used an aggregation. And this is probably why we were able to query the whole world instead of just a single small state or geo-bounded area. So what will happen here is we build this pipeline of query options where we say, match the date time plus an hour. So you give it a delta. So instead it'll find everything within that certain time. Where the quality values are 0, 1, 5, or 9, which are apparently the good values. So I lied to you earlier when I said 9 was a bad value. And then we want to group these with the ID of station. And then we get the position. And we get the air temperature. So I know that syntax is fairly MongoDB specific, but that's all that it's doing is it's just doing a typical aggregation around a set of data. So, and you could consider storing those quality codes as integers, but there's no real space savings. There could be, I'm not sure. It would really depend on the underlying Json specific implementation, and I don't know enough about that. So I'm going to change slides, and whoever can figure out what changed. So what I've done here is I've highlighted New York State. So what I've done here is called geofencing, and it gives you a way of querying without having to hit the whole world. And if in a sharded cluster, if you have things distributed in a certain way, and the geo portion is part of your sharded index, you're going to be able to hit a specific node instead of hitting all of these nodes and having them come back to you. So this is a pretty good idea. So New York is defined as 2,000 points. Thanks, Long Island. And you can actually pass that whole thing into MongoDB's query system. So you can say, find everything in this polygon. What's probably easier is to store it in another collection and then look up points that are in that polygon, because it's probably going to be fewer things to send over a network. All right, so that's that. And then we get to the operational concerns, which is my favorite part. And again, everything expressed in this is my own opinion. All this pricing data is my own and doesn't reflect the opinions of my employer. So we chose to run this on C3.8. So we run the MongoDB nodes on i2 8x larges, which have 251 gigabytes of RAM, and they come with some ephemeral storage, which are 6 terabytes of SSDs. Now, these are extremely fast pieces of hardware. You can do a lot. They have like an insane number. They have 32 CPUs. So if you run top on these things, you just get giddy. And what you can do, instead of running on a single server, is that you can run on a sharded cluster, so that each one of these becomes one of those bigger nodes. So obviously, the cost may multiply, but you can still run a single Mongo OS or multiple Mongo OSs, which are the query routers in Mongo, and still hit all of this stuff. So you have 100 R3 2x larges with 61 gigs of RAM each and then 100 gigabytes of disk. So you think about the computing power that represents, and you can take Boto, which is the AWS sort of Python API, or you can take the AWS command line tools, and you can say, spin me up 100 of these, and you just get it. Over the course of the next 10 minutes, you have that compute capacity available, so long as you let them blindly swipe your credit card. So the single server costs $60,000 a year, and the large server costs $700,000 a year. So the distributed architecture costs $700,000 a year. The question you may be asking is, why in the hell would I pay $700,000 a year for something like this? And that's actually not that much when you consider the amount of data that you're moving around and the things that you're able to do with it, and the number of scientists that you're able to support with that. Now, the other thing to keep in mind is that this is without any sort of conversation with Amazon. This is without any sort of reserved instance pricing or spot instances or anything like that. So you could probably get substantially less than that actual listed cost. I put the numbers big in red because I wanted people to go, have a heart attack. I don't really want anybody to have a heart attack. So what we do, on the single server, I can bulk load things. And so I have an importer. It was originally written in Python. But then Python, because I'm a terrible programmer, as I mentioned before, I couldn't get it to keep up with the network. So instead, I wrote it in Java. So you've seen all the lines of Python in this talk. I apologize. So what will happen is we spin up 8 threads on a C3 8x large, and we just start shoving stuff into Mongo as fast as we can get the network to take it. And so my 5th grade math teacher is probably yelling at me right now because I haven't labeled my axes. But I'm not even going to explain this because I don't have a lot of time. This is a lot easier to read. That graph is so hard to make. Excel is just the most infuriating piece of software in the entire world. So it takes 10 hours to load all of this data in, and then you have an index build time of 7 hours and 40 minutes. That's frustrating. And the reason for that is because you're having to constantly take data from memory and put it on disk in order to make room for other data from the disk to be indexed. And that whole process, even with SSDs, is just still slow. So in the sharded cluster, we get a little bit better performance. Instead of 7 hours, it takes 5 minutes. So just a little bit better. So what will happen here is we have 228,000 documents per second. And I know that you're saying, what, this isn't math? What? Arithmetic. So what happens is you actually end up saturating the network pipe, even on a 10 gigabit NIC that Amazon gives you. So that's the number of documents you can send because TCP sucks. Yeah. So then we run these different queries where we say on a single server, we want a single point in time. So I asked for July 7th, 1969, or sorry, July 16th, 1969, which is the day that we launched Apollo 11 and humans walked on the moon, which was really cool. And I don't know why I thought the weather would be interesting then. And then the station ID that I chose was Kennedy Space Center. And you'll see that the single server performs admirably, 1.5 milliseconds to return that whole set of data. And you can get a throughput of 40,000 ops a second with that query before the network becomes so saturated that it's not reasonable. And then the cluster, you can do 610,000, but the actual query performance isn't that much better. What's a little bit more interesting is going to the day the Berlin Wall fell down, or the year, sorry, Berlin Wall fell down, and you can query that whole year, one station for an entire year. So the fact that the Brandenburg Gate weather station continued collecting data throughout this entire year is hilarious and probably false. So just keep that in mind. But there are a reasonable number of data points to make one believe that it was actually collected. So what will happen here is the cluster can do a lot more operations per second, and it can return a lot faster. Here's the part where the cluster really shines for ad hoc queries, where you don't know that you're going to be doing this beforehand. What will happen is on the single server, you will run queries that will take a heinous amount of time, and it will only be able to support 1 or 2 of these operations at once. And then you go to the cluster, and it can support a lot more. So that's what you're getting when you pay for the $700,000 a year, whatever it was. So this is my final sort of slide, because I really have to hurry because I have a single minute. But what will happen, who thinks that the sharded cluster is going to finish in less than an hour? A prize goes to the person who can guess the closest amount of time that the sharded cluster takes.
60 seconds.
60 seconds, it's 2 minutes. The prize goes to this gentleman. So 2 minutes. Oh, and by the way, the maximum temperature is 143 degrees. It's in Death Valley, and it was in a year that I should have written down. So the pros are that the single server is cost effective. You can do anything that you want with the single server, and it's cheap, and it's reasonable, and you can basically run this whole thing and just accept that it's going to take a while. So if you're a poor little science shop and you can't afford the $700,000 a year, this is what you want to go for. And this is the sharded cluster. So really fast throughput, and I got to go.